Hey class, welcome back to Behavioral Statistics. We are moving into our penultimate chapter. If you're taking this course at OCCC with me, then we're covering the last two chapters that we're covering are 12 and 14. So if you're watching this and you're not an OCCC student, not a big deal at all. Just this, I don't have a chapter 13 coming for you or a 15 after 14. So just FYI. In this chapter, we're going to cover a topic called Introduction to Analysis of Variance, or sometimes referred to as ANOVA. So, by the end of this chapter, you should be able to explain the purpose and logic of using ANOVA, be able to perform analysis of variance or ANOVA on data from a single factor study, know when and how to use post hoc tests. These are just called post tests, like Tukey's, HSDs, and I may be mispronouncing this, but I believe it's Shafas or Shafes. If I'm mispronouncing it, I apologize. But those are post hoc tests that you use when you find significant results, and then we can also use n squared to measure effect size, kind of like we used effect size in previous chapters with our hypothesis testing. So the tools you're going to be needing, we're talking about an analysis of variance. So this, obviously, we're going to be focusing on the topic of variance or variability, sum of squares, sample variance, degrees of freedom, things we've talked about before, all the way back from chapter four. We'll bring in ideas we've been working with as far as hypothesis testing, and then the independent measures t-test as well, kind of some thoughts and ideas from there. So nothing too new, but just kind of reorganizing it in a new way. So anyways, here's the overview. That first learning objective, kind of when and why we would use an analysis of variance or ANOVA. It's when we're trying to measure more than two groups or populations, treatments or populations. So we're going to use sample data as the basis for making generalizations from conclusions about our population. And the advantage of this over the t-test is we can use to compare more than two means, or excuse me, two treatments. I shouldn't say means. I just mean treatments. So don't forget in the previous chapters with our hypothesis testing, we've only been working with two treatments or two conditions. Now we can go above and beyond that. So here's just an example of what that might look like. Let's say for a medication trial, we have a pharmaceutical company that's testing out a new drug to lower blood pressure. So we have three different groups. We have one group who does not receive the treatment, receives a sort of placebo of treatment just to see what the baseline is for comparison. We have a low dose treatment and a high dose at different milligrams there, and we can measure, their blood pressure over the course of 8 weeks. Does the dosage level make a statistically significant difference in blood pressure reduction? And so ANOVA is really appropriate here. We have our one independent variable, which is dosage level. That's what we're manipulating. And we do have more than two levels, placebo, low, and high. And we're comparing the mean outcome, in this case, blood pressure reduction across all three groups. And the ANOVA will tell you if at least one group mean is significantly different from the others. And if so, we then conduct these post hoc tests like the Tukey's that we'll talk about later on and figure out where are the specific differences. So visually, this is what it might look like if we have these three groups. We don't know their sample means. We might know things like their sample size, and we conduct the means, and we're going to compare them. We have their sum of squares. Obviously, the higher that sum of squares is, the more variation. But that's kind of visually what we're trying to, previously we would only be talking about maybe comparing population one and two. Now we can throw in that third and really deep dive and figure out what's kind of going on there. So some terminology that's really important for ANOVA. We're going to be talking about factors, the independent or the quasi-independent variable, the one we manipulate. That's what designates the group that's being compared. So in this case, the factor would be your dosage level. From the previous example would be the dosage level. Some would get none as a placebo, some would get a small amount, and some would get a larger amount. There's levels to our factors as well. These are the individual conditions or values that make up a specific factor. So in this case, we had three levels to our single factor. We had the placebo group, the low dose group, and the high group. And then our factorial design is a study that combines two or more factors. And that's when you start getting into multivariate statistics. But we're not going to dive into that for this course. But just know that's kind of what's happening there. And we are engaging in hypothesis testing, like the last four chapters we've looked at. We are looking at first our null hypothesis, which always says there's no difference. So in a sense, we're saying the treatment conditions have no effect on the participant scores. If we wanted to pick that, we have H0. Our mean one is going to be equal to mean two, is going to be equal to mean three. So in the population, this is the equivalent to saying that the group means do not differ from each other. We're saying there's no difference there. Our alternative hypothesis, H1, there's at least one mean difference among the populations. The treatment conditions medications do affect the scores, like being either in the placebo or the high or the low dosage does have some kind of impact on the scores. And then the shorthand, I mean, it's pretty simple. You can just say not the not our null hypothesis. How many ways can the null hypothesis be wrong? All means are different from every other mean. Some means are not different from some others, but other means do differ from some means. So I know that's a bit confusing, but this is what allows us to kind of say there's some difference going on here, and then afterwards, if there is a significant difference, we can tease it apart and really see where it's at. So why do we use ANOVA again? If we're comparing two, if a t-test compares two means, why do we use ANOVA? Basically, every time you run a t-test, you increase your alpha level by the level of the alpha you set. So if we have to run these, if we're running multiple t-tests instead of one because we have three comparisons, or we're running multiple, we're going 0.05, 0.05, and we're adding that up. So our likelihood of committing a type 1 error goes up by our alpha level each time we're conducting these t-tests. So essentially what ANOVA does is it evaluates all of those mean differences simultaneously with one test, regardless of our number of means, and kind of avoids inflating our experiment-wise alpha level. We don't increase the odds of violating our or committing a type 1 error, I should say. So it's not possible to commute a sample mean difference between more than two samples. So what we're trying to do is develop a called an F ratio. This is what the ANOVA is going to produce, and it's based on our variance instead of sample mean differences. So we're not comparing means. Essentially, we are comparing variance, and variance is used to define and measure the size of the difference among our sample means. That's going to happen in the numerator. So essentially, our equation for running an ANOVA is focusing on variance. So we have variance to define the numerator. We have variance in the denominator that measures the mean differences that would be expected if there's no treatment effect. So numerator is the variance between our sample means. Variance on the denominator is expected with no treatment effect, essentially saying the null hypothesis is true. We're going to break it down further. What we're really looking at this point is looking at between treatment variance and within treatment variance. So between treatment variance is the variability that happens from just general differences between the conditions. I'm going to show you some examples on the next slide. Within treatment variance, though, is looking at variability within each sample. So your individual scores may not be the same with each sample. So here's kind of what that looks like. Here's a variance between example. So in the case of our average blood pressure, the variation, we are going to see some reduction in blood pressure across three groups. We're comparing the mean of a placebo, the 50 and the 100 milligram group. So the medication, if it does have an effect, we would expect the group means to be different. That's going to be our variance between. So a lot of our variance between group means suggests the factor or the dosage level might be so more variance on the top level suggests there's actually something happening there versus variance within that denominator, the variance of blood pressure within each group. So among people who they all have the same dose within the group that has 0, within the group that has 50, within the group that has 100. So kind of thinking about like if we just put a spotlight on that 50 milligram group, not everyone in that group is going to have the same exact blood pressure reduction, even though they got the same dose. A number of reasons why they could have individual biology. People, have different genetics, different biology. People have different diets, stress, exercise. There could just be randomness involved. There could be measurement error. It could be all of the above. So our denominator is tracking that variance between. Our denominator is tracking that variance within. So essentially, we are trying to capture the total variability. We're looking at between treatment variance, the numerator of our F ratio, and the denominator of our variance is a within treatment. So random, unsystematic factors. We are trying to compare we're creating a ratio of the systematic over the unsystematic. So essentially, what we're looking at is F is going to be our differences that include any treatment effects on the denominator, or excuse me, the numerator, and the denominator is differences with no treatment effects. So denominator is called the error term. What it measures only random and unsystematic variability, the things that could influence our results that are not necessarily random, like we're versus the independent variable, what we're clearly manipulating. So the value of that F ratio determines whether any treatment effect actually exists. So we're really looking at two possibilities after running this F ratio. There is no systematic treatment effects, meaning those differences are entirely caused by random unsystematic factors. And so we're retaining the null hypothesis. The treatment does have an effect and causes systematic differences. In this case, we're rejecting the null hypothesis. So if the null is true, the size of our treatment effect is going to be near zero when we measure n squared later. Our F ratio is going to be near or is going to be closer to one, indicating that the difference between the treatments are random. So the closer it is to one, basically what we're saying, the numerator denominator are pretty similar. They're going to come pretty close to one another, meaning any differences there are just random. If the alternative is true, we're rejecting the null. The size of the treatment effects is more than zero. The F ratio is larger than one, and there are some kind of systematic treatment effects, some kind of significant differences there that we want to evaluate with our post hoc tests. Okay, so I just threw a lot at you. Let's go ahead and review. Decide if each of the following are true or false. First one, ANOVA allows researchers to compare several treatment conditions without conducting several hypothesis tests. And second one, true or false, if the null hypothesis is true, the F ratio for ANOVA is expected on average to be a value of zero. Think about both of these and write your answers down or keep them in your head. Pause the video and come back. Let's take a look at both of these. First one is true. Several conditions can be compared in one test. That's the beauty of the ANOVA. And then the second answer is false. If the null hypothesis is true, the F ratio will be closer to one, not zero. So here are some key terms that you need, especially when we're unpacking the formula. These notations are really critical. Like I would have this written down, and then you're going to have the formulas next to it because the formula is almost like trying to decipher hieroglyphics, and this is your translation over here. Like these notations are going to be how you translate the hieroglyphics because at first it's going to look really weird, I promise you, but if you have this near, it'll help a lot more. So our number of treatment conditions in this case is K. So if we go back to that previous example, we had three conditions. We had the condition of no drug, 50 milligrams of the drug, and 100 milligrams of the drug. So three conditions. Number of scores in each treatment. So if we use 20 participants in each treatment, we would have, number of scores for each of those treatment. You add all those up, that's going to be uppercase N. So if let's say we had 20 in each condition, three conditions, multiply that, we get 60. So when all the samples are the same size, what we're really talking about is N equals K times N times N. So if we have three conditions and we have 20 participants in each score, we just multiply that if they're the same size. Our sum of our scores, all we're doing is taking and adding up our sum of our scores. So sum of X just equals individual scores for each treatment, and that equals T, uppercase T. The grand total of all scores in the study, so adding all those conditions up, G equals adding. So let's say we have three conditions. We sum up the scores for each one. So we have a T for group one, T for group two, T for group three. We add all those up, and that gives us G. Unfortunately, not to be confusing, but there's no universally accepted notation for ANOVA. Other sources may use other symbols. This is what we're using for this textbook, and it tends to be similar to what you would see in the SPSS output. So here's kind of the structure of our way we calculate it. So remember, our F value is trying to calculate that ratio, variance between, variance within. How do we find variance between? We use sum of squares between, and we use degrees of freedom between. So again, this is where I strongly recommend that um, you have this slide kind of handy as you're working through because the more pieces of information you have, the better. Variance within is going to be sum of squares within, degrees of freedom within. Well, we have our sum of squares total that breaks down to between and within. We have our degrees of freedom, which breaks down to between and within, adding into our variance within, between, variance within. So, not to be complicated, but this is what we're breaking it down. So, if we want to look at our sum of squares total, we're going to add up all of our scores, square them, subtract that from G squared over N. So go back, make sure you have this handy while you are looking at these formula because it's going to make it a lot simpler. That breaks down to sum of squares between. Remember, we need sum of squares between in order to solve the variance between treatments. So that's going to be sum of squares for treatment means or sum of T squared over N minus G squared over N. Sum of squares within treatments is going to be the sum of all of our sum of squares inside each treatment. So it bifurcates even further. That's just to find sum of squares between, sum of squares within. Okay? And here's that formula: sum of squares total, sum of squares within, sum of squares between. And that is what we plug into these numerators. So this is very much kind of like Inception. I know it's kind of confusing. So in order to find our degrees of freedom, our total degrees of freedom, remember we need total. Total is going to be n minus 1. Remember, n is our total number of scores. So if we have 60 participants, we're going to have 59 for total. Remember I said three conditions, 20 each, is going to be total. Within treatment, degrees of freedom is n minus k. So remember, 60 minus k would be our number of treatments. So it would be 60 minus 3, giving us 57. And then between treatments, degrees of freedom is k minus 1. So if we have three conditions, 0, 50 milligrams, 100 milligrams, that's going to be 3 minus 1, giving us 2. So that's how we find. That's why I'm telling you, please, when you're going through these systematically, have this handy. Like these next like 10 slides basically have handy. And I know it's going to be kind of cumbersome and take a while to work through all that, but I promise it'll make things easier. Okay, so that's how we find our degrees of freedom. Here's a visualization too. Degrees of freedom total is n minus 1. Between treatments, k minus 1. Degrees of freedom within treatment is really just n minus k. That's another way of thinking about it. Okay, so there's another way of looking at that. Square our variance between, sum of squares between, degrees of freedom between, variance within, sum of squares within, degrees of freedom. So F really is looking at, it's just breaking this down even further. That's the original equation we looked at. Okay. Quick comprehension check. An analysis of variance produces sum of squares total of 80, and a sum of squares within is 30. For this analysis, what is the sum of squares between? We have A equals 50, B equals 110, C equals 2400, or D equals more information is needed. I'll just go ahead and spoil it for you. It's not D. But in order to find that, you're going to have to there really is three procedures you can do here. One of them is right, and the two of the others are wrong. So go ahead and pause the video, and hopefully you come up with an answer. Unpause when you feel ready. In this case, hopefully you're back. Hopefully you did the work. It's 50. We just subtract within. We subtract total from within. That's what leaves us behind the between. So remember our degrees of freedom. Excuse me, sum of squares. We have our total. Then we have our if you know the total and you know within, then you can find between. If you know between and you know total, you can find within. If you know between, you know within, you can find total, essentially, is kind of what we're saying here. Okay. So hypothesis testing, here's an example. If the hypothesis test is true, the F value will be around 1. Our F ratios are computed from two variances. They are always positive numbers. So table of F values is indicated by 2. 2, we have a degrees of freedom numerator, and we have a degrees of freedom for within. So you'll need to use that. You can pull that down from our Canvas, or excuse me, our Moodle page. And this is what you might actually see the distribution of those ratios. And then, you're going to have your 2 degree, you're going to have your ratio 2 and 15. That's how you're going to see it depicted. In this case, this is our critical value for an alpha level of 5, critical value for our alpha level of 6. Or I'm sorry, alpha level of 1. Read this number below. Sorry. Okay, so here's what this might look like. Hypothesis test, use the same 4 steps that have been in our previous hypothesis test. Choose your alpha level. You need to draw it out if you can. You're going to compute your test statistic. F is done in stages. Compute your sum of squares total, which allows us to calculate between and within. Our mean squares total, mean squared between and within, and allows us to compute F. And here's what this will break down to. So this is a way we present the ANOVA results. It helps it organize, and it allows us to direct the analysis process, and it's kind of a standard way of showing. So we have our within treatments, we have our degrees of freedom here, mean squares, we have our total here, and we have our F value here, which is much higher than 1. It's a much higher ratio than 1 in this case. So we probably have something going on there, some kind of significant result. So how do we measure the effect size? We want to compute the percentage of variance that is accounted for by those treatment conditions. The higher the number, the better. So when we publish those results, it's eta squared, I should say. It's not n squared. Sorry, it's eta. It's that symbol, it's that Greek symbol. Sorry, I should have said that up front. It's similar to the r squared we looked at in previous chapters, but eta squared is just your sum of squares between treatments over sum of squares total. And the higher that number, we're saying more variance is taken into account. So our treatment means our standard deviations are presented in the text, table, or a graph. Typically, you'll have your results are summarized. You have your F and your degrees of freedom. So we have our within and between degrees of freedom. We have our F value. We have our P level. And then finally, we have eta squared, which just shows the amount of variance. So in this case, 48.8% of variance can be explained by our treatment conditions. The assumptions, observations within each sample must be independent. Population must be normal. Populations which samples are selected must have equal variances. That homogeneity of variance we talked about, I think, in chapter 8 or 9. Sorry, I'm drawing a blank there. Violating the assumption of homogeneity allows us, maybe it might invalidate our test results. So if we find a significant result, then we want to run what are called post hoc tests. These are where we can actually compare the individual differences. The ANOVA allows us to compare them individually or individual differences simultaneously, but what we don't know where we don't know which means because we're talking about at least three groups now, so we don't know where is the mean difference between group 1 and 2, group 1 and 3, group 2 and 3, what's going on. So post hocs are follow-up tests that allow us to figure out where those mean differences are, where they're significant and where they're not. So essentially, what we're doing is comparing two individual means. This is a pairwise comparison, and each comparison does include a risk of type 1 error, and those accumulate and add onto the alpha level. So increasing our number of hypothesis tests increases the total probability of alpha each time we do it. So post hocs are ways that we can kind of control the experiment-wise type 1 error rate. They're a way of working around that. So the most common one you're going to hear about is Tukey's. It's called the Tukey's HSD, or honestly significant difference. We're getting a single value that determines the minimum difference between our treatments, means that is necessary to claim there is a statistical significance, a large enough difference that our p-value is less than our alpha value. So, and this is typically depicted as Q squared, mean squares within divided by n, so our total number of our number of participants. Our Shafa test is one of the safest of all possible. It protects us from type 1 errors. In this case, we use an F ratio to evaluate the significance of the difference between one treatment and condition. So in this case, we have mean squares between over within, calculated within sum of squares of our two groups. Okay, so let's do a quick comprehension check. Which combination of factors is most likely to produce a large value of an F ratio? Is it A, large mean differences and large sample variances, B, large mean differences and small sample variances, C, small mean differences and large sample variances, or D, small mean differences and small mean variances, or sample variances, excuse me? Think about the equation. Think about the ratio equation. That's how you're going to do it. So pause after you've thought about the equation. Think about which answer would probably influence and increase the value of our F ratio. Okay, pause. Welcome back. In this case, it's B. If we have bigger differences between our groups but smaller variation, we are going to see a higher F ratio in this case. Next one, decide if it's true or false. Post tests are needed if the decision from an analysis of variances fail to reject the null hypothesis. And then true, true or false, a report shows ANOVA results F. We have degrees of freedom 2 and 27 equals 5.36. P is less than 0.05. We can conclude that the study used a total number of 30 participants. So pause the video. Think about the different formulas we used earlier when looking at degrees of freedom. Think about why we use those post hoc tests or post tests to answer these two questions. Okay, unpause the video. I'm unpausing it now. Hopefully you have. Correct answer for the first one is false. Post hoc tests are needed only if you reject the null hypothesis. And then the second one is true, because remember, degrees of freedom total is n minus 1. And degrees of freedom, because degrees of freedom is between versus within. So we can add those two up, minus 1. There you go. All right, so more about ANOVA. The numerator of the F ratio always measures how much difference exists between treatments, and the denominator measures the difference within treatment. So that's again kind of conceptually what we're working with. And here's just kind of a visualization. We can compare experiment A, experiment B. Here we can see there's a clear difference between our treatments here. Maybe not so much, not so much. We definitely see less variation over here, more variation over here. Okay, for two independent samples, the relationship between our ANOVA and t-test, either T or F can be used, always result in the same statistical decision. This T statistic compares differences or distances between our means. The F ratio compares variances. So the relationship, really what we're talking about, F is equal to T squared. So for any value of alpha, our critical region, T critical squared is what's going to be our F critical value. All right, so if we have an F critical value 2.01, we're going to square that, and it's going to be 4.41 for our F ratio in this case. So here's the formulas again for our ANOVA, total, and then between and within treatments. So keep those handy. I would have these handy away. Like seriously, just have this slide handy. It'll be so useful. That's going to be it for this chapter. Please let me know if you have any questions or concerns. Sorry, I mean this is the first time I've recorded a video and taught about ANOVA, so please don't hesitate to send me questions if you have any. But that's going to be it, folks. See you on the other side for chapter 14. Take care.